Hi, welcome back everybody. Today I'm going to show how to do CASSCF calculations of a high-spin cobalt complex. So this is a part of the molecule that has a high-spin cobalt center here. So I am going to copy the coordinates and submit an ORCA input file. So this is the input file for CASSCF. I am using def2 SBP on all atoms, but I'm using def2 TZBP in cobalt and zinc. Then I'm using an auxiliary basis set def2J on everything, and def2 SBP/C for the correlated calculations. This basis set is required by CASSCF and other types of calculations. Then I'm using a relatively good grid. This no final grid X, you can erase it. So I've been told by the ORCA team that this is actually changing the presets that this grid X6 option is using, but in this case it's not very important. So everything is standard, but we have the CASSCF module here. So we have to define the number of electrons and the number of orbitals. So I have the structure here. The charge, the total charge is 0, and the multiplicity that I'm starting with is 4. The multiplicity is also set here, and I think that the CASSCF module overrides whatever I wrote here, but I do not know if there's a difference if I had chosen a starting multiplicity of 2. So I have 7 electrons in 5 orbitals. That's the electron configuration of cobalt 2, both high spin and low spin. And I ask for both multiplicities, the high spin, spin 3/2, and the low spin, spin 1/2 multiplicity. And then on the CASSCF you need to choose a number of roots. If you choose only one root, it would be, you would only be calculating the ground state. So if I chose multiplicity 4 and 2, but I only put one root, that would give probably an error because I'm defining 2 multiplicities. But if I only define multiplicity 4, I could calculate only one root. But I'm interested in magnetic properties, so it would not make any sense to calculate only one root. At least it would not give me the magnetic properties I need. It may give me a good starting point for other calculations maybe. So why I'm choosing 10 and 5? If you do a ligand field analysis of cobalt 2, you will know that the 7 electrons distributed in 5 orbitals give rise to 10 high spin configurations and 40 low spin configurations. So the 10 high spin configurations times a multiplicity of 4, giving total 40 configurations containing spin, and the 40 low spin times 2 gives me 80. So 80 plus 40 gives 120, which is all the ways that you can arrange 7 electrons in 5 orbitals. So I know I have 10 high spin configurations, and I know because I have studied high spin cobalt before that all of these configurations are in principle important in determining the magnetic properties. So I could have also chosen, for example, for 10 would have probably given me a good description of the magnetism of this high spin cobalt. I'm also choosing some low spin configurations, but I know that given the kind of structure, the low spin roots will not be very important. So I'm only choosing the lowest ones. But you can actually choose different types of roots, different numbers of roots, and you can see for yourself. Then this is commented out, so it doesn't matter right now. It's something that if you uncommented, you would do some ligand field analysis on this I'm not going to do it now. This is an option for the orbital optimization step. This is the option to switch to the direct inversion of the iterative subspace optimization algorithm, and this is a threshold for switching. Then what I'm doing is using the NevPT2 keyword. So this is perturbation theory that is applied on top of CASSCF, because CASSCF is the multi-configurational equivalent of Hartree Fock. And we know that Hartree Fock it's a good approximation for some things, but it's not very accurate in getting good energetics. So in the same way, CASSCF describes well qualitatively a lot of things, but in some cases it's not quantitatively not good enough because it's lacking dynamic correlation. So the perturbation theory is one of the possible ways of including this dynamic correlation, and SC is for strongly contracted is one of the options for NevPT2, but it's something that I have never really explored. Then, because I'm interested in magnetism, as this molecule has a high spin configuration, there will be a zero field splitting, and usually for octahedral or distorted octahedral cobalt-2, it's a large zero field splitting. So rel is for relativity, and do soc means do spin orbit coupling, true. So it means do spin orbit coupling calculations, include them, and calculate the zero field splitting. And G tensor true is also I want the G tensor. This will calculate both the G tensor associated with the total spin 3/2, but it will also calculate effective G tensors for the Graunsted-Kramers doublets. So then I'm requesting spin density and electron density. That's something I always do, and there's nothing else to it. This is actually very easy, and I am going to go to the out file because this calculation I already did it. It took me 26 minutes. So 26 minutes for a CASSCF calculation, it's quite okay, because basically the active space that I chose, 5 orbitals and 7 electrons, is not that large, and I'm not choosing a very large basis set. So, but 26 minutes is quite comfortable. So if we look at the output, we can see that if we look at the output, we can see, okay, first the input is copied, then the basis set information, etc. Then a set of options relating CASSCF are printed, and what is important is that there's an initial configuration interaction state check. So basically a set of configurations are built. I don't know how they are built, with which criteria. And these are basically the configuration interaction matrix is diagonalized previously to optimization of the orbitals. So this gives a set of energies. And I have different configurations that they have different energies and are composed by these occupation numbers. So I'm going to explain this a little bit better when we look at the orbitals. But basically, these are configurations that have one electron on the first orbital in my active space. I have not yet shown you how these orbitals look. Then I have 2 electrons on the second, 1 and 1 on the third and fourth, and 2 on the fifth one. And then I have mixtures of other possible configurations. This is basically because we are doing a type of configuration interaction. So we have different configurations of the electrons in the orbitals, which are mixed into given these different states. So then I have different excited states. The fact that I have these kinds of energy differences, which are more or less on the range of the UBBs, is already promising, but we are still not we don't know yet if this is a good calculation. We soon get to really high energy, so this is suspicious. But this is before starting the self-consistent field. CASSCF means complete active space self-consistent field. So, okay, we have different roots. And then what it does is it optimizes the orbitals and recalculates this configuration interaction matrix and obtains different roots. So it has this G is a gradient, is a measure of how good the convergence is. These are occupation numbers for the different orbitals, and this is, for example, is rotating orbitals which are in the active space with orbitals which are outside. After a set of iterations which went on really fast, this G number is decreasing. When it decreases enough, the CASSCF converter signals convergence, and then we basically get to the end. So this took 44 iterations. There are many more things going on than in a simple Hartree-Fock or DFT calculation. And there are a set of metrics. And then this prints the orbital energies, the orbital occupations, etc. So this is my active space. I have 5 orbitals that go from 144 to 148. Remember that ORCA starts counting on 0, which have occupations which are between 0 and 2. And if I go further, I will start having again the roots for the energy, but this time from the optimized orbitals. It found the correct orbitals. So now we see that the energy splittings are much lower, and there are many roots which all are in the UV visible range. Some of them, the first ones are in the IR range, but so basically this is looking good for the D transitions, and the same for the block of multiplicity 2. If we look at the energy of multiplicity 2, this is 30 minus 4930.84, and if we go to the first root here is 4930.90. So this indeed has proven that the high spin multiplicity was the ground state. So we have here different transitions. It tells us the ground state is the first root, the 0 root of the multiplicity 4, and then these are the excited states, and we have a set of high spin transitions, and then we have the first low spin root at around 13,000 wave numbers. We have more information and loading orbital compositions, etc. And then after all the orbitals, I have the NEV PT2 part. So it starts at some point, and for each multiplicity and root, it does a correction of the energy. So this is the longest part actually of the calculation. It becomes much slower if you increase the active space and if you increase the basis set and if your molecule is larger. And after this, we have, these are all the energy corrections for the different roots. It's a lot of information how different types of excitations have contributed to the energy. And then we have, for example, the corrected transition energy. So this would be again the multiplicity 4. The first root is still the ground state in FPT2. Sometimes it changes. Sometimes CASSCF doesn't actually guess the right multiplicity ground state, but NEPPT2 fixes that. And then we have the corrected energy. So in these energy differences are a little bit larger than in the case of CASSCF. So because magnetic properties are calculated from the composition of the states, but also from these energy differences, it's very important to have them as accurate as possible. So we have more information, and then this calculates an absorption spectrum. So these are only transitions that go inside the active space that I ask for. So for calculating UVBs, you have to make sure that you include all orbitals that contribute to the UVBs. So the DD transitions are very low in intensity, so the oscillator strength is very low. But in many metals have a charge transfer transition. So if you're only using d electrons, you're not going to get your full UVB spectrum. You have to actually see what kinds of orbitals are involved. So in that respect, it may be a very good idea to do first TD-DFT and find the most important transitions, which orbitals are involved, and then when you do CASSCF and NEF-PT2, you see that you can include those orbitals, which is not always easy because sometimes there are too many orbitals and large active spaces become very, very hard to deal with. So there's more information related angular momentum. These are spin orbit coupling matrix elements. And the interesting part, at least for me, is that I can calculate from this, I can calculate the D tensor that comes from the zero field splitting, which gives me a value. For D is 63 wave numbers, and E over D, the rhombicity parameter, that's 0.22. So these values, I don't know yet if these are correct. I have experiments on this complex which I'm analyzing and will tell me better if what is the correct value. But at least these numbers are reasonable for high spin cobalt. So I know that this value, it is reasonable. It may, I don't know if it is correct, but it's not very extreme for octahedral high spin cobalt 2. And these are contributions to the D and E values that come from different roots. So you see that the contributions come from excited roots. So if I only calculated the ground state root 0, I would not have any D and E. And then I have G matrix. There are several G matrices because it's calculated more than one way, and also we have CASSCF and NEF-PT2 results. These are, I think, all the NEF-PT2 results. So also this is the electron G matrix. This is the G matrix associated with the ground states Kramer's doublet. So I get values which are very anisotropic. So 6.49, 3.85, 2.14. Again, I don't know if these values are exactly correct, but these are reasonable values for this system. And there's a electronic G matrix from an effective Hamiltonian that calculates with a full spin multiplicity, which is what I call myself the real G matrix. The other one was an effective G matrix, and this is actually confusing that, but this is a G matrix associated with the spin 3/2. The other was the effective G matrix associated with the pseudo spin or effective spin 1/2. The people who have studied high spin ions will know what I'm talking about. If not, I will talk on a future video about magnetic properties of high spin cobalt and similar ions. So the G matrix is 2.05, 2.51, 2.76. Again, reasonable results. So here we have the orbitals, and if we look at the different active orbitals, we see that all of them are 3D centered orbitals. So these orbitals are reasonable. We have to, of course, in order to be sure of the results, we should check with different numbers of roots and different numbers of active spaces in order to see if the results are consistent and reproducible. And we should, of course, compare with the experiment. That's very important when studying magnetic properties. So I hope that this has been useful. Thank you very much.